So we've seen with Pascal's triangle that there certainly exists some sort of relationship between the binomial coefficients, which allows us to find them quite easily rather than expanding the whole parentheses out. So let's investigate this idea further about expanding binomials. If I've got 1 plus x to the power of n, then I know I'm multiplying 1 plus x by itself n times. So 1 plus x times 1 plus x times 1 plus x times 1 plus x, and so on and so on. Now, when we expand out parentheses, what we basically are doing is choosing one term from each of those parentheses and multiplying them together. And then we have to come up with every possible combination, and that would be our complete expansion. So, for example, I could choose x from the first parentheses, then a 1, then an x from the next one, then a 1, then a 1, then a 1, and I'll keep pulling out the 1s until I get to the last parentheses where I'll pull out the x, and that would be x cubed. That's just one possible way of coming up with a term. So the question is, how many other ways, or how many different ways could I have ended up with x cubed? As I say, that's just one of them. Or how many different ways can I choose 3 x's from n sets of parentheses? Now, this is something we've seen before. It's back to permutations and combinations. In this case, we're saying it's a combination because the order doesn't matter. We just simply want to get 3 x's out of those n sets of parentheses. So the answer would be NC3. Okay. This is now going to help us generalize our binomial expansion so that actually we don't need to draw Pascal's triangle. It will be NCK. So our combination, NCK, will always end up being the coefficient of x to the power of k in the expansion of 1 plus x to the power of n. Because what we're saying is we're going to take x out of k of the parentheses. So we want to choose which k out of the n parentheses that we're going to pull it out. Well, there's another way we write NCK, and we tend to use it when we're talking about binomial expansions. And instead of using the NCK notation, sometimes we use this notation, which it looks like a set of parentheses, and it looks like a fraction, but it's neither. This is just another way of writing NCK. So 1 plus x to the power of n then would equal NC0 plus NC1x plus NC2x squared, and so on until we get to our last term, NCN x to the power of n. Well, having just 1 and x isn't really useful because we want to be able to expand out any binomial. So we can extend this idea. What if it's a plus b to the power of n? Still the same pattern. The binomial coefficients will go NC0, NC1, NC2, all the way up to NCN. But what we do is we start with the first pronumeral, which is a in this case, and that'll be to the power of n. Then when we go to the next term, we take 1 off that power, but then b comes in. So I have NC1, a to the power of n minus 1b. Go to the next term, subtract 1 from the power, but then add 1 to the power of b. So we get NC2, a to the power of n minus 2, b squared. So at any point in time, we can pick any particular term, add the 2 powers, and we'll get n. So if I wanted to expand out 2 plus 3x to the power of 4, I now can write it like this. 4c0, we'll start with the first one, so 2 to the power of 4. Next term, 4c1, take 1 off the power, so it's now 2 cubed, but the 3x comes in, so 3x will be to the power of 1. 4c2, power of 2 goes down by 1, 2 squared. Power of 3x goes up by 1, so it becomes 3x all squared. And we keep going until we get to the last term, 4c4, and 3x to the power of 4. So tidying that all up, we end up with 16 plus 96x plus 216x squared, 216x cubed, and the final term, 81x to the power of 4. We're going to look at just 3 of the basic properties of Pascal's triangle. So here's a first fundamental rule. NCK will always equal n-1ck-1 plus n-1ck. And k has to go in between 1 and n-1. How do we get that? Well, I could rewrite 1 plus x to the power of n as 1 plus x times 1 plus x to the n-1. If I expand out the 1 plus x to the power of n-1 using our new idea, so it'd be n-1c0, n-1c1x plus, and then somewhere in the middle there'd be these 2 terms, n-1ck-1 x to the k-1 plus n-1ck x to the power of k plus, and we would keep going until we got to the last term, n-1c n-1 x to the n-1. Now those 2 terms that are put in the middle become quite important because remember we want to expand out and I just want to look at the coefficient of x to the power of k. So on the left hand side I know that in 1 plus x to the power of n the coefficient of x to the power of k will be nck. So there's the left hand side. On the right hand side, if I was to expand out, the 1 would have to be times the term in the second one that has x to the power of k. And that's n-1ck. The x would have to be multiplied by the term with x to the power of k-1. And that's the other term I wrote there, n-1ck-1, x to the power of k-1. So on the right-hand side, we get 1 times n-1ck-1 plus 1 times n-1ck. That's just for the coefficient of x to the power of k. But those 2 things are equal. So therefore, nck must be n-1ck-1 plus n-1ck. What we've essentially done is proven that to find any term in Pascal's triangle, we add the 2 numbers that are immediately above it. The next property, nck will always equal ncn minus k. That's just basically saying Pascal's triangle is symmetrical. And the third one, nc0 is equal to ncn, which is always equal to 1. That's basically saying every row in Pascal's triangle starts and finishes with 1. Just going to go off on a little tangent here. Expanding perfect parentheses. We know a plus b squared is a squared plus 2ab plus b squared. It's been ingrained into us now for, since when do we first see that? Year 8 or something like that. Here's a different way of thinking about it now. So a plus b all squared. What are the different ways we could write 2 pronumerals, but the only letters I'm allowed to use are a and b? I could have a squared. If you think of it as a times a, there's 2 pronumerals. I could have b squared, b times b. The only other possibility is I could have an a and a b. I'm not concerned about the order here. So ab. Well, how many ways could we arrange 2 a's? Or 2 b's for that matter? Well, there's only 1. So I must have 1 a squared and 1 b squared. How many ways could I arrange 1 a and 1 b? Well, that's 2 factorial. The number of ways we could arrange 2 objects. And so we get a squared plus b squared plus 2ab, which is, of course, the same as what we've always understood, a squared plus 2ab plus b squared. But it's the idea that I'm interested in. Because now I can say, well, all right, if I want to expand out, and it doesn't matter how many pronumerals I have, but if I want to expand it out squared, I can use that same idea. How many ways could I write 2 pronumerals, but just using 2 of the ones in those parentheses? Well, I could write an a times an a b times a b, a c times a c, and all the ways up to n times n. But then I could go a times b, a times c, a times d, a times n, but then you'd also have b times c, b times d, b times n, and we could keep going. But there'd be all these different pairings. But how many ways can we arrange them? That's still the same. Arranging 2 objects that are the same is one way of doing it. Arranging 2 objects that are different, there are 2 factorial, or 2 ways of doing it. So any perfect square will always be all of the individual pronumerals squared plus twice all the possible pairings of the pronumerals. Let's push that through to a perfect cubed. So we'll start with the same idea. A plus B cubed. What are all the different ways I could now write 3 pronumerals using just an A and a B? Well, I could go A times A times A cubed, B times B times B, B cubed. But then I could have 1A and 2 B's, AB squared. Or I could have 1B and 2 A's. So how many ways could I arrange 3 A's or 3 B's? Arrange 3 objects that are all the same? Well, there's only one way of doing that. How many ways could I arrange 2 A's and 1 B? Or if you prefer, 2 B's and 1 A. So 2 objects are the same and one's different. Well, that was 3 factorial, but then we divided by the repetitions. So divided by 2 factorial. So we get A cubed plus B cubed plus 3 lots of A squared B plus AB squared. And possibly you recognize that as our perfect cube, just written a little bit differently. Normally we see it as A cubed plus 3A squared B plus 3AB squared plus B cubed. Well, if I had 3 pronumerals in there all cubed, I could have A times A times A and so on. I could have all the possible combinations there where I use 2 pronumerals, one of them I use twice and one of them I use once. So the A squared B, A squared C, and so on. But now I have a third possibility because I want 3 pronumerals and I just use each of them once. So how many ways can we arrange these objects? Well, we've already seen that for the cubes, it's 1. And we've seen for the A squared B's and A squared C's and so on, 3 factorial on 2 factorial. Now the question is, how many ways can we arrange 3 different objects? Well, that's 3 factorial. So there's our expansion. A cubed plus B cubed plus C cubed plus 3 times all the possible pairings of 1 pronumeral squared and 1 to the power of 1 plus 6 lots of A, B, C. Let's go a little bit crazy. A plus B to the power of 4. Same idea. How many different ways can I write 4 pronumerals, but only using an A and a B? So I could go A times A times A times A, B times B times B times B, so that's A to the 4 and B to the 4. I could have 1 pronumeral I use 3 times, the other one I use once. So AB cubed, for example. Or I could use each of the pronumerals twice. A squared, B squared. So now it comes to an arrangement question. How many ways can I arrange, and I'll just use the A to the power of 4 here. So how many ways can I arrange 4 A's? Well, there's only one way of doing it. How many ways could I arrange 1 A and 3 B's? Well, that'd be 4 factorial divided by the repetitions, 3 factorial. How many ways could I arrange A squared, B squared? Well, that'd be 4 factorial over the repetitions, 2 factorial, 2 factorial. And there's our expansion. A to the power of 4 plus B to the power of 4 plus 4 lots of AB cubed plus A cubed B plus 6 A squared, B squared. Let's try this. A plus B plus C to the power of 4. And again, we'll use the same idea. How many different ways can I write 4 pronumerals, but only using the letters A, B, and C? So I could have where I just use 1 pronumeral 4 times. So A to the power of 4, B to the power of 4, C to the power of 4. I could have the situation where I use 1 pronumeral 3 times, 1 pronumeral once. And there's all our possibilities. AB cubed, AC cubed, A cubed B, BC cubed, A cubed C, and B cubed C. And we've worked out before that there's 4 factorial on 3 factorial ways of doing that. I could now have this possibility. I use one pronumeral twice and the other two pronumerals once. So ABC squared, or AB squared C, or A squared BC. How many different ways could I do that? 4 factorial divided by the repetitions, 2 factorial. And don't forget, we've still got the possibility where I just use one pronumeral twice and the other pronumeral twice, and we saw that was 4 factorial on 2 factorial, 2 factorial. Now, I'm pretty sure we've covered all the possibilities now. So there is the expansion of A plus B plus C to the power of 4. Now, don't panic. I don't expect them to ask us to do this. But what I'm trying to show here is this idea can flow through, and theoretically we could expand out anything. So 15b, don't worry, they're not going to ask you to do some of those crazy ones that I just did. But 15b, just looking at our general expansion of binomials.